and introducing Poisson Ratio, and then using rigidity modulus. Basically, here are three well-known symbols to engineering students. And we're going to use the notations like these to describe such mathematical description of the orthotropic materials. Okay, and then we see how engineering viewpoint, from engineering viewpoint, will approach to such formulations. Okay, so basically this one will be served. So use these symbols. And from here, we're going to use the engineering viewpoint to see how those problems being formulated. And so you can use your own word to describe this. Again, we want to use from starting with the engineering viewpoint to explain the same formulation of the similar type. And that is make more physical sense to me, at least. Okay. But again, in terms of the mathematics, this one is also necessary for taking care of the transformations, etc. So now for engineering viewpoint, and we have let me define the Poisson ratio. So we start with this. Let's look at particular example here. So for example, if we consider a specimen, okay, this specimen is under uniaxial loading. And let me call this is P, and this is P. And to explain the further notations, and for example here let me designate, let me align the direction of P, for example, for the illustrations, and this is in x directions, okay? And x, y, z, so using our right-hand rule, this is y direction, this is z direction. I using red color mean nothing, I just try to distinguish, and doesn't mean this important, no, just using different color for labeling purposes. So these are x, y, z directions, and this is a uniaxial loading, the loading applied in our defined x directions. And so for this case, we want to see, again, this is explanations of the same material properties from engineering viewpoint. So from here, you will have more sense, more feeling about what we are doing here. So for example, now we divide the loading. Since here we have applied the x direction, so why not we simply put the subscript here to denote that the loading is in x directions, okay? So we divide the force divided by the cross-sectional area. Cross-sectional. This one doesn't have to be rectangular. I just make it up, and that can be actually any shape. If that is any shape, I would say any shape of a uniform cross sections. So basically, this is our stress. Okay. So that is what we got. We have the stress being calculated per definitions, and now we're going to calculate strain. In the loading directions, we have a stress, and then we have strain. Strain basically is defined by the corresponding stress. Divide corresponding stress by the Young's modulus. And here we want to specify the Young's modulus is corresponding in the x directions. So that indicating the Young's modulus could be different from one direction to the other direction. Okay. And now in the loading direction, we have such a case. Now in the lateral direction, the lateral direction is basically here in terms of our uniaxial loading. That means for any direction, for the other two directions, that is normal to the loading direction, we define as the lateral directions. So for this case, either Y or Z are the lateral directions. So that means either Y directions or Z directions. So that's what people means in the lateral directions. Okay. So in the lateral directions, the strength, the induced strength. Okay, induced, that means due to the contraction, due to Poisson ratio effect, we have the strength. And from here, we know that if this is the normal strength, by definition, this is the outside view. The Poisson ratio, we know from our fundamental information, Poisson ratio basically is the ratio in the magnitude of the lateral strain divided by the loading, the strain in the loading directions. Okay, and we put a minus indicating that it's a contraction or expansion that basically is opposing to the nature of the loading. So now for this case, we can use the similar way. So basically, in this way, you can see the lateral. Okay, we simply use this one, will be good enough. Okay. So in the induced strain can be derived from here, then we can see if epsilon y and epsilon p. Okay. For example, if we have any way to measure the lateral strain, then we can do it, for example, using the strain gauge. So now we have the major quantities, epsilon y, that is the lateral strain, and divided by the strain in the loading direction, for this case, is in x directions. Okay. So here to proceed, that's going to give us estimation of the Poisson ratio. And this one, we put a minus, so basically this is our Poisson ratio. Okay. The Poisson ratio we use in nu, pronounced as nu. And for orthotropic materials and Poisson ratio in the different lateral directions will be different from the others. So here we want to give a notation to distinguish the difference. So here is the label convection, and listen this carefully. Okay. We're going to use two indices. The first index indicates the direction of loading. The second index indicates the which lateral direction you specify. Okay, so this is the loading direction. And this is the lateral direction. Okay, so in the similar way, we have nu in the same loading condition. Now we look at in the different z directions. So that one equal to minus epsilon z and epsilon x. Okay? So that is the definition or introduction of the symbol. So from here, you should be able to deduce say, if we repeat the same reasoning for uniaxial loading in y direction or in z direction. Again, for these illustrations, I apply the loading in x direction, then we have such a sense. So in this way, I would say similarly, you should be able to, if you do the experiments, you should be able to get this. This is obtained from apply a uniaxial loading in y direction, again, this is the loading directions, okay? And also, if you apply the loading, uniaxial loading in z directions, you can estimate the calculation for the Poisson ratio like this. Okay? So, I look at those symbols here, and this is the loading directions, and the second one is the lateral direction. So from here, for orthotropic materials, from engineering viewpoint, in an orthotropic material properties, we expect there's six such values there. Okay, and in a similar way, when you do the loading, you're going to employ any knowledge about the Young's modulus in y direction and z direction in major league, right? Okay. Good. And how many parameters we introduce? 1, 2, 3, and 6, and 9. Right? 9 different material properties already so far. And plus, those are the loading in the uniaxial direction. That is about the normal strength. And plus, if we do the pure strings deformation, for example, you take the same specimen, and then if you apply the loading, for example, you apply the force, something like this. Okay, let me call the P, whatever the P. And then you measure the angles. That corresponding is the string. So from string, you will have Gx, Gy, and Gz, or Gxy, sorry. Gxy, so for example, this is x plane. And repeat the same thing on the xy, on the yz plane, so Gyz. Okay, repeat the same thing in the gxz plane. So additionally, we have 3 more independent, 3 more parameters. So here in total, who can tell me how many parameters we have? 9 plus 3. I'm not treating you. That should be supposed to be 12, right? Okay, 12. Yes. Okay, 12 parameters, engineering parameters to describe the orthotropic materials. And do I make any mistake? Do you remember when we, before we derived using elasticity to derive the orthotropic material properties, and in that section, as I mentioned, is we only need is 9 at most, no more than exactly 9 independent parameters will be necessary for describing orthotropic, right? Right now here, how much? 12. What's a mistake here? No, I didn't make a mistake. Actually, out of the 9 components, out of the 12 components, the 3 are independent, so that will contribute 3, okay? And out of the 9 here, 1, the Young's modulus, 2, 3, 6, 9. Out of the 9 components, they only 6 are independent. So in this way, 6 plus 9, they make up 12. They make 9. So we're still okay. So now the issue is how do we find out these 3 dependent information out of the 9 here? Okay, so that is remaining. I want to build up for you. So that is the, I would say this is the portion A. Portion A basically is the introducing the kind of the background introductions of these things. And now the portion B is I want to explain 3 of the 9 are dependent. Okay, basically we can write up 3 more equations as a constraint for this 9. So in this way we can make up 6. Okay, so in this way, we can try to write up the stress strain. Relation. So basically, this is a description, generalized Hooke's law for orthotropic material. Okay, and we're going to start from here. So this relation, basically, we can see. I'm going to repeat the three individual uniaxial loadings to write up the relations. Okay, because here we talk about is linear elasticity, the elastic system, which means everything is linear. And if everything is linear, we can superpose the result. So the loading conditions have three possible cases. And we say this is sigma x. Due to loading, we have corresponding stress in x directions. And again, I want to have the loading in y direction, so that's corresponding is sigma y. So due to loading, we have corresponding stress in y directions. And again, here, due to loading, we have the xy, which is, oh, sorry, this is z. Sigma y and sigma z. Okay, we have such three loading conditions, and I'm going to find out is for each loading conditions, and let me tabulate, and what is the strain in x directions, y direction, z directions, and then I simply superpose those strains together. That will represent the loadings in three directions. Okay, general loading basically is the technical summations of the three cases. Okay. So from here, our goal is to write up the strain equal to something and multiply with stress. Again, here the calculation is going to summarize the individual loading of the three cases we kind of describe qualitatively there. Okay, so that is in relation. This one basically is called the compliance matrix. I'm going to find out what is the contents for this compliance matrix in terms of the symbols we define there. And keep this in mind, this compliance matrix is symmetric. So this symmetric is based upon our previous the introductions from the beginning. That must be symmetric. Okay, and then we keep that in mind, and we do this. Okay, so for this one, basically here we simply let us summarize all the calculation here. For the first row, sigma x, basically this one, the epsilon x, sigma x divided by ex, right? Okay, for this one, epsilon y, you look at the symbols there, so that's simply equal to minus xy times, would be easier, is minus sigma epsilon x, this one, okay. Minus epsilon x, which is this, and multiply with mu xy, right? Okay, so this is epsilon y. Epsilon y, we look at using this equation. Epsilon y equal to this quantity multiplied with this. And this one equal to this one, right? Okay. And this one is simply sigma x, ex, and mu xz. Okay. Now to the second loading conditions. And second loading condition, right now the axial loading is in y direction. So the normal loading in axial, in the loading condition, in the loading direction is sigma y divided by ey. Again, Young's modulus in the y direction. So now this is the loading conditions. Again, we apply Hooke's law. Sorry, we apply the definition of Poisson ratio by this. Right now, for the second case, the loading directions is y direction. So again, this is minus the axial strain, so sigma y divided by EY per definition is y directions, and of the loading direction of the lateral directions. Okay, so this one again, sigma y and EY and mu YZ. Okay, the third one, right now Z is the direction of loading, so sigma Z divided by EZ. Okay, so now for this case is sigma Z, EZ, and mu ZX. This one is sigma Z and EZ and mu Z1. Okay? So right now we take the summations here and we use the color. So right now we simply take the summations. So basically I'm going to write it out what is the summation for this one. The summation, basically the summation of the three terms that will go to the total epsilon x, go to here. Okay, so look at this one. So right now that first term is this term multiplied with sigma x, so that will be equal to 1. Sigma x multiply over this one, so sigma x over this one. The second term will be equal to minus mu yx and ey. The third term is minus mu zx ez. Okay? Good? Okay, now let's proceed. For the second term, the first term is the coefficient multiplied with minus 6, the sigma x, so that is minus xy. Ex, the second one is 1 over ey. The third one is minus mu zx and ez. And when you are taking notes, don't make any mistake, okay? Because that has a big influence. So this one is ex, and this one is minus mu yz, and ey is ez. Okay. So right now I'm going to impose the additional 3 equations, and to say that out of the 9, and we only have 6 independent. From this equation, we claim this must be symmetric. Not claim, we have shown this must be symmetric, is symmetric. So that means this quantity equal to this one. So mu yx divided by ey equal to mu xy ex. Okay? And the same thing, this quantity must be equal to this one. So that means the mu zx and ez equal to mu xz and ex. In a similar way, you can do it quickly for yourself. And this one will be equal to this one. So that will be mu zx and ez equal to, and I think I make a typo, I'm going to fix it. Which typo? This one. dy. Okay, so let me double check 1 over ex, and then mu yx ey and mu zx ez. Okay, and this one mu xy, x y, and gy z, and xz ex, and yz ey. Yeah, that should be right. Okay, so let's type it here. Okay, so imposing the three equations to the 9 independent, not 9 parameters, so out of 9 we only have 6. Okay, so that means basically basically aligned to what we start with from elasticity. That is the more practical applications. So for people to pick out those things, the first step is this. Maybe sometimes people will give you out of the 9, out of the needed 1, 2, 3, 4, 6, 7, 8, 9, whatever the 9 the parameters that people might only give you is only 6. So you need to find out the other 3. So that means you can utilize these equations. Okay, you can utilize the equations, or vice versa. I'm going to mess up the writing here. As long as, on the other side, as long as you can figure out the contents, I mean the numbers of the 6, you simply take the symmetry to fill up the 3 numbers here quickly. Good? Okay, so that is the note I want to make. And then for the remaining, this is about the normal loading. And for the string stress, and that is very straightforward. For string stress, and basically that is gamma xy equal to tau xy divided by gxy, and gamma xz equal to tau xz, and gxz, and gamma yz equal to tau yz, and gyz. And the actions on the shearing is disengaged from the normal loading. So that is a very good property. So which means when you do the testing on the shearing, you don't need to worry about will that be any induced normal load, normal stress or normal strain. No. Okay. So again, for orthotropic materials, the materials, if they deform in normal direction, they won't induce any shearing. Vice versa, if the material is under shearing loading, then such a shearing loading won't induce the normal loading. Okay, in the orthogonal, in their the principal directions. Okay, so something like this one. So combining everything together, and we might have the big matrix. If you really like, you can we can put together like this. So string y, z, gamma xy, gamma xz, gamma y. You don't need to write this, but kind of give you the ideas. So this is the matrix. And from matrix A, okay, so let me say from matrix 1. Okay, let me call this is matrix 1. Okay, so fill the context here. And then this is 0 and 3 by 3, and this is 0, 3 by 3. And for this one is G, X, Y, 1 G, X, Z, and 1 G, Y, Z. And this one multiplied with string Y and Z. Stress. And tau x y, tau x z, and tau y z. Okay, so that is a big compliance matrix involving all the stress and strain. And again, for notations, and here I pick up it directly the engineering notations. And again, sometimes people like to using a double notation. Sometimes people like to using XX, YY, ZZ. Don't feel strange, and that's just simply the notation for those symbols. Okay. And again, to another one more note before I let you go is this. These are the typically from engineering viewpoint, And keep that in mind for each of the sharing elements, that basically equal to 2 times of our epsilon, for example, yz, xz, etc. That is 2 times of the factors, kind of the bridging the communication from the 2 fields. Okay, so keep that in mind, and then probably next time we can have a few examples to demonstrate the kind of these things. Okay, thank you.